Yeah.
I just have one more.
Let's get homework real quick. What one am I looking at?
15.7F.
Ooh, we pressed it. 15.7F. For each equivalence relation below, find the requested equivalence class. So on F, R has the same size as on the power set of 1, 2, 3, 4, 5. So we're looking for all the ones that have the same size as 1, 3. Y'all with me on what one we're looking at? So we're looking for this thing's equivalence class on the set of the power set of 1, 2, 3, 4, 5. And the relation that we're using is the has the same size. Okay, so let's make sure that this makes sense real quick. What is this set?
This is the set of all the subsets of that, right?
It's a set of all possible subsets of 1, 2, 3, 4, 5, right? So now we're looking for the set of all possible subsets of 1, 2, 3, 4, 5 whose size is the same as this set. So that's just equal to. Let's see what we're going to have in there. We're going to have 1, 2 in there. We're going to have 1, 3. We're going to have 1, 4. We're going to have 1, 5. We're going to have 2, 3.
So we're going to write it like shorthand, you could say?
Not that I know of.
2, 2?
No. Why is this bad? How many elements are in this set? 1. This does not have the same number of elements as that.
Okay.
Good? Remember, duplicates in a set don't matter.
Wait.
It doesn't change the size of the set.
What about if you said X is an element of that power set where the absolute, or the cardinality of X is 2?
2, 3, 2, 4, 2, 5. Oh, you could write it with set builder notation.
Can you do that? Would that be wrong?
My gut says it goes against what the problem is trying to get you to do, which is make sure that you know how to write it out. And you keep going until you get 4, 5. And how many of these would you have? How many would start with 1? 5 start with 1, and then 4 start with 2, and then 3 start with, did I say it right? 5 start with 1, 4 start with 2. Oh, not 4 start with 2.
5 start.
Right?
5 start.
3 start with 2. And then 1 starts with.
So why?
Is that right?
That doesn't.
No, that's
make
wrong.
sense.
4, 3, 2, 1. There we go. 4 start with 1. 3 start with 2. 2 start with 3. 1 starts with 4. That's right. So there's 11 of them. Oh, 10 of them. So if you got 10 of them, you're probably did it right.
Wait, there's more.
No, there's only 10.
Okay, so we should write it not inside of the notation.
Oh, they just wanted the equivalence class, not the size set. I don't know why I did that. But yeah, they just wanted you to write out this. That's it. Easy peasy. Okay, any other questions? No? Do you remember what an equivalence relation is?
Struggled with a little homework that I remember doing.
Yeah.
what?
It's when they're reflexive, symmetric, transitive.
Perfect. It's a relation that's reflexive, symmetric, and transitive. And then what were equivalence classes?
It's a set where one element of that is all the elements that relate to one element.
Right. It's all the elements that are related to one element using an equivalence relation. You remember the one that we talked about last time was has the same last name? That's an equivalence relation, and so we split our class up into equivalence classes. Is that ringing any bells? And we'll introduce more with equivalence relations as we go along with partitions. So let's jump into partitions, because partitions and equivalence classes are really just one and the same thing. It's a different way of talking about the exact same thing. So we'll see it in action. And a partition is a really easy idea. You already have intuition for what partitions are. So let's just give you the definition and jump into it. So a partition of a set A is a set of non-empty, pairwise, disjoint sets whose union is A. So let's read that one more time and then we'll get some intuition. A partition of a set A is a set of non-empty, pairwise disjoint sets whose union is A. So those three properties.
What's disjoint again?
Pairwise disjoint means no two sets contain the same element. So if I were to partition up students into classrooms, every student would be in one classroom and only one classroom.
So disjoint, they don't have the same elements, right?
No repeating elements in different sets.
Okay. What's the difference between disjoint and pairwise disjoint?
Disjoint is talking about two sets. Pairwise disjoint is talking about a set of sets.
Oh.
A set of sets is pairwise disjoint because there's no repeating elements in any of the sets. The intersection of any two sets is empty. So an example of pairwise disjoint sets would be, think about students as elements of the set A, and the set that they're in is classrooms. Classrooms are pairwise disjoint subsets of A if A is a student body. Every student is in one classroom and only one classroom.
And it has to be a two-element set?
A two-element.
Does it have to be a two-element set? No?
No.
Okay, just wondering.
Two-element?
I'm wondering if does that has to have, if the set of the sets has to have two elements in each set.
No, they just can't be empty. So let's look at an example of a partition on a set A. So 1, 2, 3, 4, 5. Let's look at this Let's look at this set of subsets and see if this is a partition. So we've got the set 1, 2, 3, 4, 2, 5. Is this a partition of A?
No,
Why not?
because there's two twos.
Right. Two's in there twice. Doesn't work. Next. Is this a partition of A?
Yes.
Yeah.
You sure?
Well, we don't know. We're really freaking
I know. So think about it. Read that definition clearly.
Yeah.
Well,
Yeah?
sets.
Everyone thinks that this is a partition?
Well, it says whose union is A, but it looks like that.
The union of everything in there, does that give you back A?
Yeah.
Yeah, it's perfectly fine. Alright, next, P3, is that a partition?
Yeah.
No.
No, yeah,
Oh,
no.
no.
No, why not?
It has the
As
empty
you
set.
said.
There's an empty set in there. Let's look at another one. P3, is this a partition?
Yes.
Mhm.
Yeah? Okay, P4, is that a partition?
Mhm.
No.
Why not?
So union is in
Alright, P5, is that a partition?
A. No. Well, yeah. Yeah.
Oh, sorry about
P5.
that.
Well, P5 is the
Yes,
same thing
it
as
is.
P2.
Yeah, P5 is the same thing as P2. Good. And P6, is that a partition?
No.
No, why not?
Because it has an empty set.
As an empty set. Wonderful. So a partition, pretty straightforward idea, right? And you'll note, and here's the big parallel that we're going to be making. Taking a set and splitting it up into a partition is the same thing as taking a set and splitting it up into equivalence classes. So we're going to see how equivalence classes and partitions really capture the same idea. That's going to be one of our main focuses. Okay? So just keep that in mind as we're going through. Maybe it was bad that I said that. Maybe I should have just introduced it when I came. Anyways, continuing. Alright, so if R is an equivalence relation on subset A, then the equivalence classes form a partition. Okay? So let's look at some set A, the numbers 1 through 10, and let's look at an equivalence relation. We'll look at the is equivalent mod 3 relation on A. You remember the equivalent mod 3 relation on A?
Isn't it congruent mod 3?
Oh yeah, what did I say? Equivalent. Congruent, thank you. That's congruent.
Are there other mod numbers where it's not congruent, but it's not equivalent? Or is it just congruent?
No. It's not just congruent and just mod as an operator. We'll get to more mod stuff as we go. So let's look at the different equivalence classes using this congruent mod 3 relation on this set A. 1, 2, 3, 4, 5. So let's look at the equivalence class for 1. What are all the elements in A that are equivalent to 1 mod 3? They're 1, 4, 7, and 10. You remember how to do this? You do? Is this just obvious?
I'm not remembering.
Yeah, so let's piece it back together. How do we know if x is in here? How do we know if a number is equivalent to 1 mod 3?
When 3 divides the difference between.
When 3 divides the difference is one way to think about it. The other way to think about it is divide by 3, and do they have the same remainder? Those are both perfectly valid ways to think about it. So 1, when you plug it in there, 1 minus 1 is 0. Does 3 divide 0? Yeah. Plug 4 in there. 4 minus 1 is 3. Does 3 divide 3? Yeah. Plug 7 in there. 7 minus 1 is 6. Does 3 divide 6? Yeah. So 7's in there, etc. And you'll notice it just increments by 3. Similarly with 2. 2 is equivalent to 2, 5, and 8. And then 3 is equivalent to 3, 6, and 9. And then if I were to continue and do 4, 4 would just give me the same thing that 1 did, right?
Right.
And then we're repeating after that. So you'll notice every element in A shows up in one and only one of those, right? So if we look at the set of equivalence classes, we just formed a partition. Is there something weird? Well, that was pretty weak. I was like more forward than up. Okay, so now let's prove it. This was just an example to help us understand this idea. Let's read the idea one more time. If R is an equivalence relation on a set A, then the equivalence classes form a partition. In other words, every element in A will be in one and only one equivalence class. That's all we're saying. Right? Yeah. Okay, so let's do the proof now. Oh, sorry, that's not what we're proving.
Can you, how do you prove that?
How do you prove this? Well, first off, everything is in an equivalence class because everything is in its own equivalence class, right? Then you show if two elements are related, they're in the same equivalence class, which is what we did last time. So this is actually a recap from last time, where we ended last time.
Okay.
Okay? So that's what that was. That's not something we're proving. What we're proving is, well, let's introduce the notation, then go over the proof. So, let P, kind of a weird, fancy looking P is the symbol that we use to represent partitions.
It just has a bigger curve? Or?
Yep, just an extra curve on the top. So let fancy P be a partition on A. So it's a set of subsets of A satisfying this property. They're all disjoint and none of them are empty, and the reunion together gives you back A. Good? So let P be a partition on A. We denote the is in the same part relation by this symbol.
Same part.
In the same part. Oh, sorry, I didn't mention that. These sets inside the partition we call parts. That make sense? Okay. So the is in the same part relation we denote with this symbol. And what does that mean? If A and B are in the same part, are related by this relation, that means that there exists a set in the partition, with both A and B in it. So maybe a simple example will help put it all the way through. Let A be 1, 2, 3, 4. Here's a partition on A, right? So 1 and 4 are in the same part. 2 and 3 are in the same part. 1 and 2 are not in the same part.
Right. Okay.
That's what we mean by the is in the same part relation. So now what we're going to prove is that this is in the same part relation is an equivalence relation. Which means if it's an equivalence relation, its partitions are equivalence classes. Which is a big focus of all this. So, let's go over it. So if P is a partition on subset A, then the is in the same part relation is an equivalence relation. Good? So we need to show it's reflexive, it's symmetric, and it's transitive. So let A be some set, and let P be the partition on A. First thing we need to show is it's reflexive. We need to show that every element in A is related to itself. So let X be some random element in A. We need to show X is related to itself. Now, since P is a partition, then there has to be some part in P containing A. Okay. I suddenly switched from... I went back and forth between A's and X's, sorry. That was weird. Okay. Restart. So we're showing that this is an equivalence relation. So first thing we're going to show is it's reflexive. So take some random element out of A. Our job is to show that that element is related to itself. Or in other words, it's in the same part as itself, which almost sounds obvious right out the door. So first off, since big P, or fancy P, is a partition, then there must be some part in there such that X is in that part. How do we know that? Yeah, P is a partition on A, but what's the property of a partition that guarantees us
Its union is going to be
its union is A? A partition has to union up to give you back the set A. So any element in A has to be in some part. Does that make sense? Okay. So then, obviously, X is in the same part as X. So the only weird part of that was to make sure that X was actually in a part. And then obviously X is in the same part that it's in. That part's easy. We just need to make sure it was at least in a part. Does that make sense? So we know it's reflexive. Now let's move on to symmetric. In other words, we need to show that if X and Y are in the same part, then Y and X are in the same part. So let X and Y be elements in A where X and Y are in the same part. So if X and Y are in the same part, then that means that there exists some part P such that X and Y are in that part.
right.
And Y and X are in that part. And so Y is in the same part as X. And so it's symmetric. Good? Pretty straightforward thinking? Nothing weird? Alright, let's do transitive. So to show something's transitive, we need to take three elements, call them X, Y, and Z in A, where X is related to Y and Y is related to Z. We need to show that X is related to Z. Okay, so since X is related to Y, and since Y is related to Z,
In the same part as.
yeah, in the same part as is a relation. So since X and Y are in the same part, and since Y and Z are in the same part, then there has to be two parts, namely P and Q, such that X and Y are in P and Y and Z are in Q.
Right.
Good with that logic so far? Okay. Now, since Y is in P and Y is in Q, and since our partition is pairwise disjoint, then P has to equal Q. Does that make sense? What does it mean for the set to be pairwise disjoint?
That means Y has to be in one.
Every element's in one and only one set. So if Y is in P and Y is in Q, and y is in one and only one set, then y is in P and Q. Or then P and Q are the same set. Okay? That's all we're saying there. So P and Q are really the same set. Therefore, Z is in P, because E was in Q. And so, X and Y are both in P, or in other words, X and Y are in the same part. And so it's transitive. Good? Okay.
We recording?
I sure hope so. I figured out why it stopped recording last time, by the way.
What was it?
I got a phone call in the middle of class, and so that cut it off. And then Dystonia happened to mention it like a couple minutes right after it went off, and so almost everything's online. There's only like a couple minutes missing. So you have all that, just so you know. Anyways, so we've got this idea of partitions, and we're going to use partitions to help us count, right? Because we have lots of trouble counting, so we need all the help we can get. So let's see how it helps us count. First off, let's introduce a problem that hopefully we all know how to do, and then make it a little bit more convoluted. So how many ways can we rearrange the letters in the word word?
4 times 3 times
4 factorial, right? You have 4 options for the first letter, and then 3 options for the second letter, then 2 options for the third letter, then 1 option for the last letter. So 4 times 3 times 2 times 1, which is 24 options, here they are. Do we need to recap that more? 6 times 4. Right?
Right.
Alright, we're good? Okay. So, that's the type of counting we've been doing so far. How many ways can we rearrange the letters in the word word? Now the types of problems we're going to be doing is, how many different ways can we rearrange the letters in the word hello to get different words? Now, why is this a little bit different? If we think about one of these L's is small and one of these L's is big to help us think for a second. So pretend that was a small L and that was a big L. Then how many different ways could we do it?
You could go, well, 5 factorial.
5 factorial ways, right? But in those arrangements, we would have a hello that looks like this, and we would have a hello that looks like this. When you make that L big again, then those 2 hellos are the same. Right? So for any arrangement of the letters you pick, there's 2 ways of doing it. In other words, right?
Yeah.
So if I were to write out all the arrangements of hello, and I wrote out all 120 of them, 2 of them would actually be the same. Right? And 2 of them would be the same for any of the different arrangements I made. Right? So, the idea that we have here is, let's create an equivalence class where we group together hellos that actually come out the same when you make that L big again. And let's just count the equivalence classes. Okay? Have I lost you so far? So, for each arrangement we make, we counted it twice basically. We just count 5 factorial. And we count each arrangement twice. Right? So if we think about equivalence classes capturing the same arrangements where if we make the L's big again, then they look the same. Then each equivalence class is going to have size of what? 2. So there's 120 total arrangements.
What's the relation?
The relation is when we make the L big again, it gives the same word. So if we think about one of those L's is big and one of those L's is small, if we think about those L's as somehow different, and we ask how many arrangements can we make, it's 5 factorial, but then when we make that L big again, if it gives us the same word, then they're related. That's the relation we're thinking of here, right? If I make that L big again and that L big again, then those hellos look the same. But if I keep one small and one big, then those are different. Right? So if I think about each of those L's as distinct letters, there's 5 factorial ways I can do it. Then when I make those L's look the same again, that gives me equivalence classes, each equivalence class having 2 elements in it. So the big punchline here is that we have 120 total arrangements, but for each of those 122 are the same.
That does not make sense. How?
Let's maybe start with a smaller example and come back to
Two out
hello.
of 120 that be the same.
No, for each particular arrangement, there's 2 that give it. There's 2 that give hello, spelled out.
Right.
So let's look at, for example, let's look at a smaller one. Let's do big C, little c, A. How many arrangements can we make of those letters? 6. We can do big C, little c, A. We can do little c, big C, A. We can do big C, A, little c. We can do little c, A, big C. We can do A, big C, little c. And we can do A, little c, big C. Right?
Okay.
Now, if I ask you how many different arrangements can we get from the letters C, C, A, where there's no distinction, then that makes these 2 the same. That makes these 2 the same. That makes these 2 the same. All right, we started to click what I've been trying to say.
Yeah.
So when you ask me how many arrangements can I make of this, in my head I think about it this way, and I think they're 6 factorial. But then if I break those up into equivalence classes, where when you make those C's big again, they give you the exact same thing, then each equivalence class has 2 elements. So there's 6 ways I can do it, divided by how big each of my equivalence classes are, gives me 3. So there's 3 different ways I can arrange these letters. Does that make sense?
Yeah.
So, seems so pointless.
So how do you know what the size of the equivalence class each time?
Right, we'll get to other examples.
Okay.
But just make sure simple examples make sense and we'll move forward. So this example makes sense. There's 3 ways I can rearrange these letters, right? What about with the word hello? How many different ways could I rearrange those letters? And get different words each time. 60. There's 120 ways I can rearrange the letters if they were different. The size of each equivalence class, giving me the exact same word, is 2. 60 over 2 is, or 120 for arranging letters of hello, and then 2 is the size of the equivalence class, giving me a total of 60. So you're counting the equivalence classes instead of counting the individual words. Does that make sense?
Kind of. What I'm kind of confused about is that only applies for that one example. So why are there only 60 instead of 119?
No, it doesn't.
No, for each arrangement of the letters hello. So give me an arrangement of hello. We could have had L, L, H, E, O. There's an arrangement of hello, right? But when I counted the 5 factorial here, I counted this 2 ways. I counted this as if it were L, L, H, E, O, and I counted it as if it were little l, L, H, E, O.
Right.
I counted both those. So for any arrangement you have, I counted it twice when I counted 5 factorial.
Mm-hmm.
And so if you think about, gives me the same word as a relation, both these are in there. Right?
Right.
So we're counting the equivalence classes, and how many equivalence classes are there? That's how many elements there are divided by the size of the equivalence class. So there's 120 elements, with 2 elements in each equivalence class gives us 60.
Mm-hmm.
So you're counting equivalence classes. That's what you're counting. Does that make sense?
You're counting, so what would you say you're counting when you count the arrangements?
We're counting equivalence classes. So it's how many arrangements could I have made if these L's weren't the same? 5 factorial. And then how many of them actually do give me the same word? 2. So gives me the same word is my equivalence relation. And when I apply that equivalence relation to the set, then I'm counting equivalence classes. I'd have 60 equivalence classes. I would have 60 of these that give me 2 different arrangements each time.
So it's like saying you're counting all the relations on the.
I'm counting equivalence classes.
Okay.
Where the relation gives me the same
So
word.
there's 60
Okay, but
equivalence classes.
why? That makes no sense. Why would they? How many ways to rearrange letters H-E, little l, big L-O? That doesn't make
Well,
sense.
how many ways to arrange the letters in H-E-L-L-O where it gives you a different word? So in other words, swapping those 2 letters doesn't count. That's not a different word. So how many nonsense words could I create with those letters? Is another way of asking it.
What?
Yeah, that makes sense.
How many unique arrangements could I create with those letters?
Unique arrangements?
Yeah, so I can't say swap the 2 L's, oh, there's a different one. Because that's not different.
Right.
It's still just H-E-L-L-O. So that's what we're trying to count. And how do you count that? You pretend that they were different, count it, which is 5 factorial. And then you say, now, how many times did it actually give me the same one for each of my counts? 2.
2 for every.
And that's going to be the general way that we do it. We say, what's the size of the set divided by the size of the equivalence class gives us a count.
Saying arrangements is like the same thing is like saying equivalence classes.
Yeah, when we're counting
Okay, so
the arrangements,
The
we're creating equivalence classes to do it and counting equivalence classes.
bottom number is pretty much
The size of your equivalence
the
class.
size of
How many arrangements actually give you the same word?
the letter. With how many letters there are? That are
No,
the same.
not necessarily.
If
So
there
we'll
was
see an
3
example
L's,
with
if
3.
there was 3 L's,
Yeah, we'll move on to 3.
wouldn't it be divided by 3?
No. So let's move on to an example with 3. So you all good with this one's 60 is the answer?
Yeah.
Yes.
Okay, so let's move on to a more convoluted example. How many different arrangements can I make with the letters aardvark?
8 factorial.
Yeah, so if we thought about each of those as different, so instead of A, and A again, if we thought about that as A1, A2, and A3, those A's as different, then that would have been 8 factorial, right? But unfortunately, they're not different. So when I take a particular arrangement of those letters, how many ways actually give me that same arrangement?
3.
No. The answer is 6. So I could have had A1, A2, all those letters, A3, then those letters. I could have had A1, A3,
Oh.
all those letters, A2. I could have had, you see what I'm doing?
Mm-hmm.
A2, A1, A3. I could have had A2, A3, A1. And then finally I could have had A3, A2, A1, and A3, A1, A2. Oops, I just wrote 1 instead of A1. Where do you fill the missing letters in between?
Huh. That makes sense.
So it's actually over the size of the equivalence class factorial. So this is 8 factorial over 3 factorial. But in general, you think about it as the size of your A factorial over the size of one of your parts factorial, because each of your parts are the same size.
What about your R though, because you have two R's, do you not count that?
Oh, we have two R's. Thank you, I didn't notice that. Perfect. So we actually have a R1 and a R2. So now we're in trouble. We didn't count all these right.
Did they just add right in?
Yeah.
Now, for each of these arrangements of A, I could have chosen R two ways.
Oh boy.
Right? So it really was, instead of A1, A2, A3, I could have done this two ways. It could have been A1, A2, R1, dV, A3, R2. Or it could have been A1, A2, R2, A3, R1. Right?
Right.
Oh, so that means there's 12.
Yeah. So it's 8 factorial over 3 factorial times 2 factorial. In fact.
Right.
So if there were 3 R's, that would have been a 3 factorial as well.
Mm-hmm.
Good?
Mm-hmm.
So the size of each of the equivalence classes we would get for a particular arrangement is 12. And there's 8 factorial total arrangements. Therefore, unique arrangements gives us 8 factorial over 3 factorial times 2 factorial. And then I strongly recommend reading through the author's conversation on this, because he'll probably give you a different way of thinking about than I did. That might be more intuitive. So now, binomial coefficients. You're probably all fairly familiar with the binomial theorem. Yeah? No? Never heard of it? What's that?
Binomial theorem.
I don't know.
So
we
it's
mean that.
It's for expanding out things that look like this. X plus y to the some power,
Right.
like 4. And so this is going to be something like, let's see, 1 times x to the 4 plus, what is it going to be? Is that 6? 1,
How do you do that?
4. 4x cubed, you're going to learn how. Y to the 1 plus 6x squared y squared plus 4x to the 1 y to the 3 plus 1 y to the 4.
Right.
So when we say binomial coefficients, we mean these numbers.
Right.
Because notice that figuring out those numbers is a hard part of this problem.
Mm-hmm.
I know what my x's do. They count down starting at 4. 4, 3, 2, 1, 0. And my y's count up. Y to the 0, y to the 1, y to the 2, y to the 3, y to the 4. And so the hard part of expanding this thing out is just coming up with what those coefficients are.
Mm-hmm.
And that's what we mean by a binomial coefficient. All right.
Yeah, we learned this.
The central problem we consider in this section is the following. How many subsets of size k does an n element set have? Okay. So that's what we mean by binomial coefficients. That's the idea that it turns out we're going to capture with this idea of, we call it choose notation. He's going to call it a binomial coefficient. Oh, well, I'll just write up what he has and discuss it. So binomial coefficient, let's see. Definition. Let n and k be natural numbers is n choose k is the number of k element subsets of an n element set. Okay, this is going to feel really, really weird when we first start talking about it, and you've probably seen a formula for what this actually equals before with factorial symbols in it. No? You've never come across this?
We might have, I can just, well, we might have to show
No, we
this.
haven't.
And then the idea that this captures the same meaning as these is something that we're going to capture right at the end. So if this feels completely disassociated with that, that's fine. Alright. So let's make sure we understand what this is trying to capture though. This is trying to capture the number of k element subsets you can get from an n element set. So let's do an example real quick. If I say 4 choose 0, how many 0 element subsets can you get from a 4 element set? 1. The empty set. The empty set is the only 0 element subset you can get from a 4 element set.
How? Having an empty set in all 4 spots?
Okay, let's look at an example of a 4 element set.
Okay.
1, 2, we're not counting anymore.
Exactly.
Well, we are counting,
That's
but we're
exactly
counting
what
something
I
different.
thought.
Okay, so
No, I
here's an
have
example
0.
of a 4 element set. How many 0 element subsets are there of this thing?
Oh, 1.
This is the only 0 element subset of that thing. There's only one of them. That make sense?
Yeah.
Let's do another one. Let's see how many 1 element subsets there are of this thing.
4.
1.
We got a 4 and a 1. How many 1 element subsets are there of a 4 element
Five.
set?
5.
Okay, that was our
No, it's 4. It's 4.
Oh, no, yeah, it is.
It's 4. Not sure how you guys made that leap. There's a set containing 1, then there's a set containing 2, then there's the set just containing 3, and then there's just a set containing 4.
We were thinking this out with you. We were leaving the empty sets one.
So there are 4 1 element subsets you can make from a 4 element set. Alright, now let's push the brain a little bit more. What's 4 choose 2? How many 2 element subsets can you make from a 4 element set?
I want to say 4 factorial. I don't know.
No. That's how many different ways you could arrange all those.
Is it?
So I'm creating a 2 element,
Is it 2 factorial?
I'm creating a 2 element subset.
Right.
What?
Is it 4 times 2? 8?
Almost. How many 2 element subsets? 12, but now you accidentally
16.
counted
Did it count?
twice.
Oh, yeah. So, what, 9?
No?
For every number, there's 3.
I mean, you could almost have written these out a lot quicker.
Yeah.
Yeah. Well, we have to figure out the way eventually. Without writing them out.
Well, I'm going to start writing them out since you're not seeing it like I thought.
Is it just 6?
It's 6! How'd you get that?
Okay, cool. I did 1, 2,
Oh, 'cause it's
1,
divided by
3,
2.
1, 4, 2, 3, 2, 4, 3, 4.
Oh, so you just counted them directly.
It's kind of, it's just like over there.
That's perfectly valid. There is 6. Another way that you could have thought about it is, I have 4 options for the first element, 3 options for the second element, but now order doesn't matter, so I need to divide by 2. So 4 times 3 is 12, divided by 2 is 6. That's how I think about it. But 6 is correct. So it's 6. So 4 choose 2 is 6. Alright, let's look at 4 choose 3.
4 choose 3.
There's 8.
Sorry, how many 3 elements That's how you read this
I see,
notation.
yeah.
We'll get to it.
Okay.
It's 4s, you say top, choose bottom. 4, choose 3.
Okay.
You have a 4-element set. How many ways can you choose 3 elements out of
Okay.
it? Is intuition. 8, no.
Not 8.
Notice every time you choose 3, how many do you leave behind?
1.
1. So instead of saying, which 3 am I going to take, you can ask, which one am I going to leave behind? So instead of choosing 3 elements to take, you can just choose 1 to leave behind.
So
And it's the same thing.
20.
That helps.
4.
What?
4.
4!
Frick yeah, I'm good at this.
Frick yeah! Right? You can take everything but 1, that's 3 elements. Everything but 2, that's 3 elements. Everything but 3, that's 3 elements. And everything but 4, that's 3 elements. There's 4 ways to do it.
Huh.
Just like when you were thinking up here, you could take 1, you could take 2, you could take 3, you could take 4. Here you're thinking, I can take everything but 1, everything but 2, everything but 3, everything but 4.
So what
You
about-
see the parallels between these two?
Yeah, but like what about the second one? How do you think of that way?
Well, you can't because it doesn't have a counterpart. Because the last one is 4 choose 4,
Which is 1.
which is 1. There's only one way to take everything. Just like there was only one way to take nothing. So those two are the same, those two are the same. That one's a little different.
Wait, really?
Right.
Yeah, picking 3 and leaving 1 and picking 1 are the same thing. Picking everything and picking nothing are the same thing.
Can we do another example?
Well, the reason I chose this example is so that you can see those were the coefficients.
Right, I see that. I'm just.
Yeah, we can do another example. Let's do it with 5. So maybe it helps to have the set written up here. 1, 2, 3, 4, 5. And let's look at it. What's 5 choose 0?
1.
1? Alright, what's 5 choose 2?
10.
10. How'd you get 10?
2. 2 lists.
So smart.
How'd you get it?
Because I was going here, but also I know how to do it. It's
4
just,
3. You can have. Not 6, 6.
Not 6. It's 10.
Well, the issue is I already know Pascal triangle. I'm trying to figure out how to do it.
Oh.
so
Well,
there's 5 options for the first one.
4 options for the
4
second
options
one,
for the
but then the
second.
order doesn't matter, so divide by 2.
Oh,
It's
okay.
giving you 10.
Okay.
So that one's 10. Whoa, we skipped 5 choose 1. Sorry.
Yeah, you're crazy.
5 choose 1, we all know is
5.
5. 5 choose 2, we just found out is 10. Alright, now what about 5 choose 3?
20?
5.
No, no.
How's that wrong?
No, understanding.
What'd you say?
How's that wrong?
I don't think you said the wrong number.
I said 5.
No, that's wrong.
Oh, 3.
No.
No, no.
5 choose.
How many?
5 choose 3.
Oh, yeah, sorry.
Is
5 choose 3. How many 3-element subsets can I make from a 5-element set?
5 elements for the first one, 4 elements for the second, 3 for the third. Is
There's
that?
a much easier way to think about it.
I'm missing the easier way.
No.
Or you could use everything but 2 5 times. Is that?
No. You have to leave 2 elements behind.
You have to take 3
And leave 2.
and leave 2.
So you can leave 2 elements 3 different, not 3 different ways.
How many ways can you choose 2 elements to leave behind?
5.
3 times.
No. No. 10.
10!
Oh, yeah.
Choosing 2 elements is the same as choosing 3 to leave behind.
Okay.
Choosing 3 elements is the same thing as choosing 2 to leave behind. Yeah. And then 5 choose 4 is
Oh.
5.
5. And then 5 choose 5 is
Okay. This is starting to make
One.
more sense. This is starting to make
starting to click in your head.
Oh, we do 1 more for it. I mean,
Sure.
Okay.
Let's bump it up to 6. It's getting out of control. All right, What is 6 choose 0?
1.
1. The empty set. What's 6 choose 1?
It'll be 120 divided by 3. Is that right?
That's not gonna happen, no. It's 6.
Yeah.
6.
How many
Why'd you
one
even
element
do that?
subsets?
I was thinking 6 choose 2. I'm thinking 6 choose 2. My bad.
Oh, you were skipping to 2.
Okay.
Okay, 6 choose 1.
6.
It makes perfect sense, it's just 6, right?
Yeah.
It's all the one element subsets. Okay, 6 choose 2.
12.
15.
What's my guess?
No, it's not 12.
30. No, 20. Not 20. I should. We did this 3 times. I should do it right now. Is it? It's not 40, is it? Is it 20?
No.
15.
What?
15.
15?
Yes.
Yes.
I said that.
Oh, you did?
Yeah.
I didn't hear you.
Okay. So there's.
There's.
Oh no. Oh, I see. Okay, because it's 30 divided by 2.
Right.
Okay.
6 options for this one, 5 options for this one. We don't want to count the order, so that's divided by 2.
Okay.
Right.
Alright, 6 choose 3. You're going to get this one.
Is this 40?
I have to think about this one. Okay, got it. What'd you say?
40?
No. What?
I said 40.
No.
Okay, so there's 6 options for the first one. There's 5 for the second, 4 for the third, and then you want to
It's
not care about the order. So it's, you're dividing it by 6. Well, it's 20.
20! Exactly! Good job! You see how we did that?
Not 20.
So we're doing 3 elements.
Right, 6, 5, and 4.
There's 6, 5, and 4, but then we don't care about order.
Divided by.
So there's 3 factorial ways to order it. So you divide by 3 factorial. So 6 times 5 times 4 divided by 3 factorial.
120 divided by 6.
So 3 factorial cancels out with 6, leaving 5 times 4.
Wait, why divided by 3 factorial?
Because sets don't care about order. Right?
Divided by 3, maybe?
No. There's
Divided by 2?
when we do 6 times 5 times 4, we counted how many 3 element lists can we make. Right?
Mhm.
But with sets, order doesn't matter. So we divided by how many of those gave us the exact same elements, just in different order. And that was 3 factorial.
Okay.
In other words, we counted, when we do it this way, 6 times 5 times 4, we counted this one. We counted, let's not use 6, 5, and 4 since that's what we're counting. We counted 1, 2, 3. We counted 1, 3, 2. We counted 2, 3, 1, 2, 3, or 2, 1, 3, 3, 2, 1, and 3,
1, 2.
1, 2. We counted all of these, but notice if you view these as sets, these are all the same set. This has the same as that, it's the same as that, it's the same as that, it's the same. So we counted each one of those 6 times, each of the same set 6 times.
So why is it 3 factorial? instead
That's how many of these
6?
there are. 6, 3 factorial, same
So
thing.
why 3 factorial?
There were 3 ways that gave us, there were 3 ways to arrange this one, 2 ways to arrange this, 1 way to arrange this. It's counting the arrangements of the exact same set.
Okay.
I don't know. You have another way to say that?
No. Well, I just remember it made sense when we were doing it, when we studied factorials like that. We're doing the same things when we study factorials. When we do that.
Yeah, kind of. Anyways,
And then it's just going to be the flip of that.
6 choose 3. Now it's 6 choose 4.
14.
6 choose 4.
15.
15. 6 choose 5.
6,
6. 6 choose 6.
1.
And do you know Pascal's triangle?
Yes. Is there a theorem for that, or is it just a conjecture?
We'll prove that this gives you the elements of Pascal's triangle, but that's another way that you figure out these coefficients real quick. You start out with a 1, and then you go to the next row on each side of the numbers you have and add up whatever's adjacent above. Sounds weird right here, but once you get started, you'll get the pattern. So next one, I look here above, there's only 1, look here above, there's only 1. Okay, now for this row, we have 1 is all the elements on either side of this. If I add the elements on either side of this one, it's 2. If I add the elements on either side of this one, it's 1. So you build a pyramid as you go.
Okay.
So here it's going to be 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. You see what I'm doing?
Yeah.
So what's next?
1, 6, 15, 20, 15, 6, 1.
Goodness.
Which is exactly what these are. And you'll notice these coefficients right here are this line. So if it's to the power of 1, it's this line. To the power of 2, to the power of 3, to the power of 4, to the power of 5, to the power of 6, to the power of 7, to the power of 8. Pascal triangle. Gives you these binomial coefficients.
That's actually starting to make more sense. Because before I just used it, I didn't know why it now makes sense.
Well, there's still no reason yet that you should suspect that these numbers magically give you these numbers, magically give you these numbers.
It kind of makes sense because the power of 4, I mean, it's like when you're expanding, because when you're expanding that by hand, you're putting down log endings in just different ways.
Yeah.
And so it's like, it seems like just a faster way to count it up.
Well, we will come up with a way that we use these as counting, which is what we're going to have to do to make these make sense, because this is counting subsets of a particular size.
So it doesn't like make perfect sense, but it's starting to make sense.
Well, that's good. All right, so that's an introduction to binomial coefficients. And hopefully you're getting pretty comfortable with that choose notation. Jeez, that is just a black whiteboard.
Yep.
Erase more than anything.
It wasn't that bad last week, was it?
It keeps getting worse and worse. I keep washing it with water and I keep getting after them. Alright, let's go over some special cases in general for the choose notation. Maybe I'll write it over here with this. Anytime I have n choose 0 is always equal to
1.
1. N choose 1 is always equal to
N.
n. N choose n is always equal to
1.
1. And n choose n minus 1 is always equal to
N.
n.
Okay.
See those special cases? Assuming that n minus 1 isn't 0. Because otherwise it's up there.
Then you could also either make it, you could continue to make an expression an equation.
We will come up with an equation. So those are the special cases that are going to help us get our foot in the door. So, let's see. Proposition 17.5. Let n be an integer with n greater than or equal to 2, then n choose 2 is
Wait, what?
yeah.
Okay.
Will you explain the summation notation one more time?
Yeah. Give me a second to figure out what this author's trying to say. Let n be an integer with n greater than or equal to 2. Then n choose 2 is equal to 1 plus 2 plus 3 all the way up.
Didn't we do something very similar to that?
Yeah, n minus 1. We've designed these.
Yeah.
Okay, yeah, let's go over sigma notation real quick. Okay, sigma notation. Let's do it real quick. So you put somewhere to start at with a dummy variable, somewhere to end at. It's very common to use k as your dummy variable. So k will start at what?
1,
1. We'll end at.
2, 5.
And what should our expression be?
What's
K squared minus 2.
what's the expression?
Just
So it's like something you
What
plug
you put the
into.
number through.
so an expression, if you think about an equation, what's on a particular side of an equation?
An
An expression.
Oh.
So you put an expression that has k as a dummy variable.
And then you just plug in all the k's.
Yeah. So this is equal to, what do you get when you plug in 1? Negative 1. Plus, what do you get when you plug in 2? 2. Plus, what do you get when you plug in 3? 7. Plus, what do you get when you plug in 4? 14. Plus, what do you get when you plug in 5? 23.
Right.
And then whatever that sums up to is what that is equal to.
Okay.
Okay. So,
So what about the other notation that we looked at in the lesson that we did last week? We didn't really go over it, but it was in our homework.
I don't know what notation
It
we're
was
talking about.
the big U.
Oh, union?
Universe.
No, it was. It's this. Like, I don't remember us talking about
Oh, sorry. It is union.
that. That's union?
Yeah. So I might have something like A1 equals a set 1, 2. A2 equals a set 2, 3. A3 equals a set 4, 5. Then I would say the union from k equals 1 to 3, that's not supposed to be there, just use like that. The union from k equals 1 to 3 of a sub k is equal to a1 union a2 union a3, which is equal to 1, 2, 3, 4, 5. That's all this.
Okay.
Sorry about that. So it's probably like doing a union across equivalence classes to get back to A or something like that, to start with. I don't know, I can help you with the specific context, but in general, that's what it is. Alright, back to wherever I was. Yeah, it's another thing that he just notes and doesn't prove. I don't understand why he keeps noting things and not proving them. So, he makes notes of things that he doesn't prove. I don't know if it's because he expects you to do it later. But, he says, for n greater than or equal to 2, n choose 2 is equal to 1 plus 3 plus 5. Oh, no. Skipping, sorry. Is equal to 1 plus 2 plus 3 plus ... plus n minus 1. Which can also be rewritten as the sum from k equals 1 to n minus 1 of k.
Oh, okay.
Good?
Yeah.
So let's check that in our examples real quick. 6 choose 2. He's saying that this is equal to 1 plus 2 plus 3 plus 4 plus 5.
Okay.
He's saying n choose 2 is equal to 1 plus 2 plus 3 all the way up to n minus 1. The sum of those. Which is what this notation is, right?
Mm-hmm.
So our example here for 6 choose 2. What's 1 plus 2 plus 3 plus 4 plus 5? 15. For
7 choose 2.
yeah, 7 choose 2. What would that give you?
21.
No. 8. Oh yeah, sorry.
It is 21.
It is 21.
Okay.
I was thinking for 8 when I said 7. Right, just add 6 to that. 7, choose 2. 6 plus 5 plus 4 plus 3 plus 2 plus 1. Okay, so he just states it. So we'll just state it for now. I'm hoping we're going to come back and actually do something with it. And then the other thing he states is something that we've already noted in 17, oh, I skipped 17.6. Oh, 17.6 is this example. He also notes that n choose k is equal to n choose n minus k. That's the symmetry that we noticed.
That's 7.7.
Yeah. So this is a symmetry that we already noticed. Choosing k elements from n can be viewed the same as choosing k elements to stay behind from n.
Mm-hmm.
Right? So
That doesn't make sense. Isn't n minus k going to be a lesser number than k?
n minus k, it can be. It can also be a greater number.
But it's going to be the same thing. Oh, okay.
Right?
Yeah.
So pick two numbers for n and k, as long as k is not greater than n. If you pick n equal to 5 and k equal to 4, what are we saying? We're saying 5 choose 4 is equal to 5 choose 5 minus 4, 1. Right? Okay. Here's another way, blah, 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 we already noted that.
Wait, no, that doesn't make sense. Because okay, that's a good example, but also like, can you plug in something else? 2 and 4? No,
2?
No. 3 and 2.
3 and 2. So let's look at 3 choose 2.
Wait,
And is
no,
that the same thing as
5 and 3.
3 choose 1? 5 and 3. So,
No. 5 and 5. 5 is it.
and 5's k.
So we have 1K. Okay, that makes sense.
Good? See the symmetry? And the way to think about it is choosing k elements from a set is the same as choosing to leave behind n minus k elements.
This makes more sense because you read it out of 2. It was like, here's what this kind of is. We didn't choose, but it wasn't. It was just here, plug it into your calculator, and it will work.
Yeah, not a big fan. Okay. Calculating and choose k. Thus far we have calculated, so they took a long time to calculate 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. So let's write the binomial theorem in general now. No, we can just prove it by here right now. Sorry. Okay. Let n be a natural number. Then x plus y to the n is equal to the sum from k equals 0 to n of n choose k x, does he do that between n and the n minus k, x to the n minus k, y to the n, or not to the n, to the k. So this is called the binomial theorem. This is exactly what we've been doing, but now let's work it out. What case did we do over there? 4. So let's, some of your homework problems are probably going to start out with plug in the case n equals 4 to the binomial theorem and expand it out. Something along those lines. So let's do that real quick with the binomial theorem. So what does this say for x plus y to the 4? That's saying x plus y to the 4 is equal to, start at k equals 0 and plug it in, and you plug in 4 for n, right? So we're saying 4 choose 0, x to the 4, y to the 0, plus, now plug in 1 for k, 4 choose 1, x to the 3, y to the 1, now plug in 2 for k.
Yeah, see, we've done this.
Now plug in 3 for k. Now plug in 4 for k. Good? Simplify the expression. What's 4 choose 0? 1. What's y to the 0? 1. So 1 times x to the 4 is just x to the 4. Plus, what's 4 choose 1?
3.
4.
All right.
X cubed y to the 1.
Oh, I see.
Okay.
Don't base your thinking off of Pascal's triangle.
Right, based off of logic.
Think about it in terms of sets.
Right.
That's the right way to think about the simple. I promise, if you get comfortable thinking about it that way, the applications are just,
Did make sense.
you'll blow people's minds with how fast you come up with the answers to things, because it's real easy to think about it in terms of sets.
Really?
Yeah,
Okay.
it's an easy way to do it. So just get comfortable thinking about it in terms of sets. It makes it like you can start answering all sorts of questions that don't seem like they're related, right? It's like, if I randomly kick 3 people out of the student body, how many ways can I do that? The answer is a number of people in the student body, choose 3.
Yeah.
And if you keep trying to think about this symbol in terms of just these coefficients in Pascal's triangle,
Have big problems.
answering that question you don't even relate it to. When really, what the symbol is the answer to that question.
Right.
Does that make sense?
Mm-hmm.
Okay. Anyways, next one. 4 choose 2?
6.
6. Right? 1 plus 2 plus 3? 6. Or 4 times 3 divided by 2? 6. So 6, x squared, y squared, plus 4 choose 3 is just
4.
4, x to the 1, y cubed, plus 4 choose 4 is
1.
x to the 0 is,
1.
and so we just have y to the 4. And there we go. That's what you get when you plug in 4 to the binomial theorem. Pretty neat.
That's awesome.
So that's what the binomial theorem is in general. And let's see how they continue with their proof. This result explains why y choose k is called the binomial coefficient. The number n choose k, or the numbers n choose k, are the coefficients that appear in the expansion of x plus y to the n. Now we're proving it. The key to proving the binomial theorem is to think about how we multiply polynomials. When we multiply that, that's how we're proving that. Maybe we'll take a break right there and I'll get started on the proof of the binomial theorem, and then when you come back, we'll prove the binomial theorem. jump through it and I'll finish with you. So, we want to prove that when we expand this out, we get this exact thing. Okay? With me so far? Do you understand what the problem is asking us to do? In other words, we tried it for the case where n is 4, and we tried it for the case where n is 5, and it happened to work. It doesn't work in general. Can we always use this expansion? Good with the question?
Yeah.
Okay. So, first off, think about how we multiply it to help us understand the problem. So when I do x plus y squared, then that's x plus y times x plus y, right? And the way that we can view this is, I can take either x or y from here, and I can take either x or y from here. So if I do x and x, I get x squared. If I do x and y, I get xy. If I do y and x, I get yx. And if I do y and y, I get yy. So notice it's the same thing as thinking that I have 2 options for the first element and 2 options for the second element, giving me a total of 4 ways to do it. Good? You see how it's like counting lists? Let's see it again for the case when it's 3. So if I have x plus y cubed, then we can do that as x plus y times x plus y times x plus y. And I can choose x times x times x, that's that one. Or I can do x times y, there's that one. Oops, there's that one. And I can keep taking all the different combinations. And so you know before we even think how many terms am I going to get.
What?
How many terms?
Yeah, when I multiply this out, how many terms do I get?
6.
3 factors.
8.
3 times
3.
I have 2 options for the first element, 2 options for the second element, 2 options for the third element.
Okay.
Right?
Okay.
So there's 8 of these. 1, 2, 3, 4, 5, 6, 7, 8. Good, I didn't miss one. Right?
Mm-hmm.
And so that's a way that we can think about this. X plus y to whatever n. It's counting the number of n element lists we can make where their elements are x's and y's. Is that making sense?
Mm-hmm.
When I have x plus y to the n, that is counting all the n element, or that's giving us all the n element lists we can make with x's and y's. These were all the n element, these were all the 3 element, you can view these as all the 3 element lists we can make with x's and y's. You can view these as all the 2 element lists we could have made with x and y. So it's the sum of all those lists. So, notice though that when we collapse these, we get repeating terms.
Right.
Right? So if I were to collapse this, I have an x squared y here, and I have an x squared y here, and I have an x squared y here, and I get 3 of those terms. So the question then becomes, how many terms in x plus y to the n have exactly k x's and n minus k y's? In other words, how many of a specific term? Right? That's what we want to count now. Now, obviously, we want the answer to be n choose k. That's what we're saying we get here. We're saying when you expand this out, you get n choose k of this term.
Okay.
Is that making sense? It's kind of dense.
I'm missing kind of what step 4 is saying.
So this gives us, so we know that this gives us all the possible n element lists when you have x's and y's to choose from, right? Here are all the 3 element lists you can make when you have x's and y's to choose from.
Oh, okay.
So now the question is, when we collapse these, how many terms in here have exactly k x's and n minus k y's?
So, okay. And,
So let's say that up here, n we know is 3, but let's say k is 2.
okay.
So how many have 2 x's and 1 y?
And 2 is just what you're, it's what you're wondering about, like what's the, I'm trying to think like, what does the 2 mean? I'm kind of moving with this. what? So you're thinking 3, choose 2, right? But
Yeah.
what's the significance of the 2? Like, why do you want that?
I was just doing that as an example. So, look, we're saying when you plug in 3 to here, x plus y to the 3, when you use the binomial theorem, what does that give you? That gives you 3 choose 0 times x to the 3, y to the 0, plus 3 choose 1, x squared y to the 1, plus 3 choose 2, x y squared, plus 3 choose 3, x to the 0, y cubed, right?
Okay.
So, this is how many terms had 3 x's and no y's. This is how many terms had 2 x's and 1 y. This is how many terms had 1 x and 2 y's. This is how many terms had no x's and 3 y's.
Okay.
And so,
Oh.
okay, you start to see it? So that's what we're interested in. So we already know that this gives us all the possible combinations of 3 element lists you can make with just x's and y's, right? So then the question is, if we were to count all the ones that have exactly k x's and n minus k y's, would we have gotten n choose k?
Right.
Does that make sense now?
Mm-hmm.
Okay, so that's what we're saying here. So the question becomes, how many terms in x plus y to the n have k x's and n minus k y's? And we want that answer to be n choose k, because then our formula is correct. Right? We're good? Okay, so now what does n choose k capture the idea of?
How many k number of elements are in n? Is that right?
It's how many k element subsets
Subsets.
we can get from an n element set.
Right.
And so we want that to somehow, that coefficient, we want that idea of counting subsets of n element sets to also capture the idea of how many of a particular term show up in here. Does that make sense?
Yeah. So this is a combinatorial group.
Yeah, it's a counting proof. Okay, da 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 da. Let's see. We can specify all the lists with k y's and n minus k x's. Oops, I did it backwards from him. He said k y's. Same thing though, right?
Mm-hmm.
And n minus k x's. The reason he does that is because in our formula, x is to the n minus k, y is to the k.
Right.
Okay. All right. We can specify all the lists with k y's and n minus k x's by reporting the position of the y's. Okay. So let's look at an example real quick and then make sense out of this. So let's say that I want scratch work to the side. Let's say I want to do all the ones that had 2 y's in them, right? So k is 2, and n minus k is 1. So I want to count all of these that have 2 y's in them and 1 x in them, and I want it to be 3 choose 2. I'm trying to show that that's 3 choose 2. I'm trying to show that that's the same thing. That's counting all the... And so the way the author is saying to think about this is make a set where you count the positions of the y's. So which ones are we counting? We're counting all the ones that have 2 y's in them. So we're counting this one, we're counting this one, and we're counting this one. Right?
Only 2 y's?
Yeah. All the ones that have 2 y's in them
And 1x.
and 1 x. So he's saying the way that you can think about this is think about we put a we track the indices that the y's show up at. Because we want the number of them to be 3 choose 2. That's what we want it to be.
What's an indice?
So let's look at this one. We had a y show up in the second position and the third position. Right? Let's look at this one. We had a y show up in the first position and the third position. Oops, that's a 3. And then let's look at this one. We had a y show up in the first position and the second position. Jeez.
Okay.
You see it?
Yeah.
So when we count the positions that the y's show up in, we're counting all the 2-element subsets of our 3-element set. There were 3 possible indices that the y's could show up in. We chose 2 of those indices for them to show up in.
Okay.
So, if we're looking at, am I losing you on that line?
Not really. Is an indice just one of those terms?
Oh, sorry. The index of this x is 1. The index of this x is 2.
Oh.
The index of this x is 3.
So the
Or this
indice
y
is the
It's its position in the list.
Okay.
Okay, so yeah, remake that connection. See how 2, 3 captures this one? 1, 3 captures this one? 1, 2 captures this one?
Mm-hmm.
Okay. So, for example, n equal to k, blah, 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 blah. And then we're basically done.
Okay.
The number of lists with k y's and n minus k x's is exactly the same number as k element subsets of 1, 2 through n. So let's think about a more intuitive way to represent this for you. So, I wish I had a better way to say this. It's supposed to look like that. How can I say this better? So, okay, let's think about it one more time. So x plus y is counting all the possible n element lists with x's and y's in it, right? So we're making these lists, and there's n elements in there. All the way up to n, whatever n is. In this case, n is 1, 2, 3, 4, 5, 6, 7. Right? And we have 2 options for each of these, x or y, x or y, x or y. Now, we're saying that n choose k, we're saying that this should count all the ones that have k y's and n minus k x's. So give me some k for y, real quick. 4. So let's say that k equals 4. We're saying that n equals, in this case, 1, 2, 3, 4, 5, 6, 7. 7, and so n minus k is 3. So let's say we're trying to count all the terms, all the lists of x's and y's that have exactly 4 x's in them, or 4 y's in them, sorry, and then 3 x's, right? And he's saying the way that you can envision counting those is you can pick 4 indices for the y's to go in. So, if we think about the set of numbers 1, 2, 3, 4, 5, 6, 7, then these are the possible indices that we can put a y at. And you can pick 4 of those to put a y at. Right? I can put a y here if I want, a y here, and a y here. That's 4 y's. That's the same thing he's saying as choosing the subset 1, 2, 3, 4, 5, 7. So, in every way that we can arrange these 4 y's in this list, it's the same thing as picking 4 elements from the set of indices. So, n is the number of indices, and k is the number of y's that we're choosing. So we're choosing 4 indices to put a y in. Is this not making sense?
intuitive sense. I'm trying to think of it.
I mean, writing out the rest of this proof isn't the part I'm really worried about. You can read the authors. I want this part to make sense.
The proof makes sense. You're showing that n choose k is like.
Big picture one more time. X plus y to the n gives you all the possible n element lists made up of x's and y's. This is all the possible 3 element lists made up of x's and y's.
Okay.
How many of those 3 element lists had exactly 2 y's in it? 3. That one, that one, and that one. How did we count that? We said we had 3 indices to choose from to put the y. We had to choose 2 of them. So there were 3 choose 2. We had 4 indices we had to put the y. We had 7 indices to choose from. There was 7 choose 4. You have n indices to choose to fill the y in. You have to choose k of them. N choose k.
Mm-hmm.
So there's n choose k terms that have exactly y k's in them. K y's in them. Not y k. You follow that? Is it putting you to sleep? That's the idea. Crazy. So, maybe the example he does right after this will help spin a bit. Expand x plus y to the 5 and find all the terms with 2 y's and 3 x's.
Wait a minute. This is me. Oh, well, you use proposition 17.7. Do you?
No, 17.7.
Never mind, you don't.
So we're looking at, was it to the 5?
Yes.
So we got x plus y to the 5, and we're looking for which terms?
X and y.
How many?
2 y's, 3 x's.
Okay, so when we expand this out, how many terms will have 2 y's and 3 x's? Is that what it's asking?
Yes.
Find all the terms with 2 y's and 3 x's. It doesn't say count them, it says find them. So what are all the possible terms with 2 y's and 3 x's?
1, 2, 1, 3, 1, 4, 1, 5, 2, 3.
Well, we can do x, 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 y, y. That one's obvious, right? We can do x, x, y,
Y.
x, y.
You can move each one
It's a
all the way
lot, it's
through.
a lot.
There's a lot of them.
Pair it up with 1, 2, 3, 4, 5.
It should be that many.
You can do.
Yeah, there's only 10.
Yeah.
But the point is, what he's saying is, so here we were picking 2 y's out of 5, and we put them at indice 4, 5. He's trying to draw the parallel between writing all these out and the fact that you're going to have 5 choose 2 of them.
So he's saying that there's 5 choose 2 of each of those things.
So he's saying that there's 5 choose 2 ways that there's 5 choose 2 terms that will have exactly 2 y's in them if your power was to 5.
Right. And then there's going to be.
And then this was equivalent to choosing 3, 5. Right? And for any 2 element subset you can give me,
Okay, but would that be the answer?
he's saying write all these out. So let's think about it this way instead. Let's think about all the 2 element subsets of 5, and then we'll write the corresponding one this way. So we know that we could have 1, 2, right? 1, 3,
1, 4, 1, 5.
1, 4, 1, 5, 2, 3,
2, 4, 2, 5.
2, 4, 2, 5, 3, 4, 4.
3, 5.
Oh, 3, 5, thank you. possible 2-element lists, 2-element subset you can get from a 5-element set with the numbers 1 through 5. And then the corresponding, all the possible x, y terms you could get with exactly 2 y's would be, we could have y in the 1 position, y in the 2 position, and then x, x, x. We could have y in the 1 position, y in the 3 position. We could have y in the 1 position, y in the 4 position. We could have y in the 1 position, y in the 5 position. We could have y in the 2 position, y in the 3 position. We could have y in the 2 position, y in the 4 position, etc. You see the parallel? That's what he's saying. And I'm going to go get another marker because this is getting terrible.
So therefore they equal the same thing, basically.
Well, this wasn't part of the proof. This was just an example using the proof afterwards. Oh, am I getting a call? That's probably.
That's actually my phone.
Oh, it is? Yeah. Okay. Well, we're basically done. Maybe we'll power through.
We're basically done. Still not trying to pay.
Well, the next bit is Pascal's triangle, which is this scene right here. All he notes is exactly what I already told you, which is that you could rewrite the triangle as the top one, 0, 2, 0. Next we could do 1, choose 0, 1, choose 1. Next we could do 2, choose 1, 2, choose 0, 2, choose 1, 2, choose 2. Next we could do 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3, etc. Right? And it's giving you the same thing. 0, choose 0. How many 0-element subsets are there of a 0-element set?
1.
1. The empty set is the only subset of the empty set. How many 0-element subsets are there of a 1-element set? 1. The empty set. How many 1-element subsets are there of a 1-element set? 1.
You said it.
1. How many 0-element subsets are there of a 2-element set?
Right, yeah, I get it.
So you see how expanding this out will just give you these exact numbers right here.
Yeah.
And then Pascal's identity. Pascal's identity comes from, well, I shouldn't say it comes from this, but it's a way to think about calculating this term from this term and this term. Because this is the sum of those two things, right?
Yeah.
So I'm saying when you write this out, maybe I'll write one more row here and then write out Pascal's identity so that you can see it better. 4, choose 1, 4, choose 2, 4, choose 3, 4, choose 4. In other words, this is always the sum of those two. This is always the sum of those two. That's always the sum of those two. That's always the sum of those two. Right? That's exactly how you create this triangle. So Pascal's identity in general is n choose k is equal to n minus 1 choose k minus 1 plus n minus 1, n minus 1 choose k. So let's see what this is saying with the triangle. In other words, we're saying, I don't know, pick one, 4, choose 2. Saying 4, choose 2 is equal to n minus 1, k minus 1, that's this term, 3, 1, plus n minus 1, k, 3, 2.
Right.
So this is just saying that this term is equal to the sum of the two terms above it. Notice both those are above it because instead of n, it's n minus 1. Instead of 4, it's 3 and 3. And then this is the one to the left of it. This is the one to the right of it. The one to the left has one lower. The one to the right has the same. The one to the left has one lower. The one to the right has the same. See it? And obviously that doesn't work for the ones at the very edge. Huh?
Oh, yeah.
It doesn't work. And how would we do that in terms of a counting proof?
I don't know.
Are you just dying?
This is.
Show us how.
Well, the way you think about it, what are these counting?
All n elements in the k element.
Well, that.
Yeah, this counts what?
The number. No.
All k elements,
In n.
all k element subsets
Subsets.
of an n element list.
That's correct.
And the way that you can view this as a counting proof is you can say this, let's see how I can say that right. That's not a good way to say it. Let's see, how do I think about this? If you've got to choose, oh, here's the way I think about it. So, think about an n element list. We'll think about the case 1, 2, 3, 4 to help us think about it. And let's say I want to know how many 3 element subsets you could get from that. So I want to know 4, choose 3. I want to know how many 3 element subsets can I get from this list. I say that you can get all the ones that you can get if I don't let you use 4. That's what this term's counting. I take away the last term and say all the ones you can get from that one. That's backwards. I want this backwards. I mean, talk about this one first and then this one. Okay? So notice that n minus 1 choose k. That's how many subsets you can get if I take away one option from you, right? So if I take away this 4, so we're maybe write this out and then say what each one captures. So this is equal to 3 choose 2 plus 3 choose 3 in this case, right? Okay. So I'm saying this term right here captures the idea of I take away the last one from you. So I don't let you choose 4. So how many 3 element subsets can you make if I don't let you use 4?
1.
That's 1. And then how many can you get if I force you to use 4? So you have to use 4. So now you only get to pick 2 more out of these 3.
What? You only get to pick 2 more?
Yeah, so if I force you to, so we're looking at 4 choose 3.
Okay.
If I force you to use 4, there's only 1 that you can use. That's 1, 2, 3.
Oh.
And then if I set now what this one's counting is, so this one's counting I don't let you use 4. How many can you get? Just 1. This one's counting I force you to use 4.
So it's not an option.
So that's not an option. You have to use 4. So now you get to pick 2 more to pair with the 4 out of those 3. You can pick the 1 and the 2 to go with that 4. You can pick the 2 and the 3 to go with that 4. Or you can pick the 1 and the 3 to go with that 4. So it's 6 options. I'm missing something. What am I missing?
I don't know what's confusing me.
It seems to me like they don't let you use 4 at your time.
Am I counting wrong? Did I plug something in wrong?
3 over 3
That doesn't
No, that's right.
is 1.
4 choose 3. What is 4 choose 3? It's 5, right? Oh, which is what we were getting. Why was I thinking 7?
I don't know.
What?
Okay. Because you compare those two with the 4. You compare those two with the 4. Let's see. How many 2-element subsets can I make from a 3-element set?
3.
3. Oh, and 4. Oh, the answer is 4.
What are you doing?
What?
Sorry.
The answer is 4.
I got confused, and now I confused all of you.
No.
Maybe I didn't confuse all of you. Let's go over it one more time. So I'm saying n choose k. So we're trying to prove this formula using a counting proof. We know what this counts. N choose k counts all the k element subsets from an n element list. I'm saying that this one counts all the k subsets you can make when I don't let you use the last element. And then this counts all the ones when I force you to use the last element. So let's look at it up here. So when I have 4 choose 3 equals 3 choose 2 plus 3 choose 3, I'm saying 3 choose 3 is a number of ways you can make a 3-element subset when I don't let you use 4.
I know,
There's only one of them.
So it's like saying, all the ways together that you can use the last element and don't use the last element, and of course there's all the ways there are.
Yeah, so this is forcing you to use the last element. This is don't allow you to use the last element. So this is not using the last element. This is you are using the last element, which counts all of them. Does that make sense? Does that finally quick? A little bit. Then let's go over it again.
That part is.
4 choose 3. This counts all the 3-element subsets you can make from the list 1, 2, 3, 4.
Right.
I'm saying we can count that 2 ways. We can count all the ones where I force you to use the last element. Oh, sorry. That's not this one. That's this one. So let's restart because I keep changing the order that I do these. 4 choose 3 is all the 3-element subsets you can make from a 4-element list. And I'm saying the way that we can count that is all the lists that don't use the last element and all the lists that do use the last element.
Okay.
So let's start by looking at all the lists that don't use the last element. All the lists that don't use 4. How many ways can I pick 3 elements from that list? 1. So 3 choose 3, there's only one way to do that. And I say that this is the number of ones I can make where you do use 4. So 4 is not an option anymore. You don't get to choose whether or not you use 4. I'm forcing you to use 4. So now you get to choose 2 more options out of these 3 to pair with that 4. So you can choose 1, 2, which gives me the list 1, 2, and then 4. You can choose 1, 3, which gives us the list 1, or the set 1, 3, 4. And you can choose 2, 3, which then gives us 2, 3, 4. So you can choose 2 of these last 3 to use, and then we pair that with the 4. That's what this counts.
Okay.
So this counts all the ones that don't use the last element. This counts all the ones that do use the last element. And then we've counted all of them. That's what this is counting. This counts all the k element subsets you can make that don't use the last element. So it wasn't an option. We took that option away. Right? This counts all the ones where we force you to use the last element. So you don't get to choose the last element because we're forcing you to use it, and that gets rid of one of your options. So now you only have k minus 1 options left. You don't have k options. That make sense?
Yes.
That's how the counting for that flows.
Awesome.
And then you can read through his, but that's the logic of it.
Okay.
Okay.
The end?
Nope. Formula for n choose k, and then the end.
Well, there's lots of paths too.
Huh?
There's lots of paths there too.
What does coefficient mean?
A coefficient is what comes in front of the variables. X and y are variables, that's the coefficient. It's constants. It's not variable.
Okay.
It's what comes in front of the variable. Coefficient. I don't know. I don't know another way to explain it. And then the formula for n choose k, which you've probably seen before, is equal to n factorial over n minus k factorial times k factorial. And we can make sense of this doing exactly the type of thinking we were doing before. So let's pick an example of one that was kind of hard to calculate and you calculate it. So let's say we've got 13 and we're going to choose 6. There's a pretty messy one, right?
Yeah.
So how did I say to think about that? I said we think about that as we have 13 options, right? Or sorry, we have 6 options. 1, 2, 3, 4, 5, 6. We have 13 options for the first one, 12 options for the second one, 11 options, 10, 9, 8, right?
Yes.
To pick my 6 elements, I have 13 options for the first one, then 12, then 11, then 10, then 9, then 8.
Yeah.
Right? Now, what did I accidentally count? I counted all the different ways that I can order those as well.
And divided by.
So I need to do 13 times 12 times 10. So I need to do 13 times 12 times 10 times 9 times 8. And then I need to divide by what?
Well, times 11. Right?
7 factorial.
Oh, sorry. 13 times 12 times 11 times 10. And then I need to divide by what?
I said 7 factorial, but I know it's wrong.
6 factorial, right?
Okay. Sure.
Why is that right?
Because I accidentally counted all the different orderings of these as well.
Okay.
And sets don't care about order.
Wait, where did that come from?
So 13 times 12 times 11 times 10 times 9 times 8, that is all the 6 element lists I could make when I have 13 choices, right?
Now you gotta find the sets, not the lists.
And I need to find the sets, not the lists. So I don't care about order. So here I counted about all the different orders and the different arrangements. Sorry, that wasn't a good word choice.
Okay, so how do you find the denominator? It's not the denominator, it's the divisor, but is the number of
Terms factorial.
terms there are
Uh-huh.
factorial?
Uh-huh.
Okay, great.
And you'll notice that this is exactly equal to 13 factorial over 13 minus 6 factorial,
6 factorial.
6 factorial. Because what is 13 minus 6 factorial?
Once upon a time.
7 factorial?
No. Oh yeah, 7 factorial. Thank you. But then, oh, that's not the question I meant to ask. What is 13 factorial over 7 factorial?
Do not know.
6.
So if we write out 13 factorial the long way, that's 13 times 12 times 11 times
Oh, right.
10
Oh.
times 9 times 8
Oh.
times
So
7
that's-
factorial
Oh.
over 7 factorial times 6 factorial, right?
Right.
And then cancel those out, and that's exactly what we have here.
Right.
Right.
So this formula is a consequence of exactly the way we were thinking about it. This is how many lists we could make, the m factorial over the m minus k factorial. And then we need to divide by how many orderings we can make, which is what that k factorial is. Okay?
Yes, and.
K and n. Wow.
Oh, okay, this is kind of making sense on a little bit.
So that's the formula. And you could also prove Pascal's identity using this formula, which we will do later in this class. Because we'll do a proof of the binomial theorem using proof by induction. It's a better way to do it. I don't like counting proofs, particularly. Okay, and then the last type of question that we have here is lattice question, which is just an application of this in an interesting way.
Another one?
It's just an example of stuff we've already talked about. It's nothing new. It's just a way of thinking about something. So if I have some grid, and I need to get from this corner to this corner, how many different paths
So many.
through there can I get?
Okay.
How many ways are there to do it?
Bunch of different ways.
Wait.
Well, how can we think about it though?
It'll be like,
There's 3
my work.
Okay.
Let me think.
There's two terms. No.
Seven. 70.
Does this include crossing over on corners, or does it have to go?
You can only go up and sideways. Sorry, I didn't specify that, did I? And I also didn't specify something else. No backtracking. Sorry. A lot of rules I didn't specify. So now let me tell you the rules clearly. So the goal is to get from here to here as fast as possible in as short as path as possible. How many paths can you do that?
One.
No. Here's one path. You won't find a path shorter than this. I can go up all the way and then over all the way.
70?
Right.
And then I could have gone up, over, up, over. I could have gone up, over, up, over.
Right.
Isn't that still the same in the end though?
No, it's a different path.
No, those are all different paths.
Well, I'm saying as far as how many steps you take is,
Yeah, they're all taking 8 steps.
so you get there's.
Assuming all these are perfect squares. 8 steps. You're going to have to go up 8 times and you're going to have to go to the right. Or sorry, you're going to have to go up 4 times and you're going to have to go to the right 4 times.
That's 9 steps. You go up 4 times, over 2, so that's 6, 7, 8, 9.
Right.
What?
That's 9 steps.
Am I blind?
The third way you did it.
Oh, I didn't make a perfect square, did I?
No, you didn't.
No, you didn't.
I meant to. Keep changing the problem, you guys. There we go. But it still was the same multiple times. So every time I had to go up 5 times and over 4 times. Could have calculated it for that, but we'll just do this. Because that's what happened so far.
How do you calculate it with the other one?
Same thing. Should we do the other one
No,
instead?
no, no.
I want to do it both ways.
Let's just figure this one out.
Let's just figure this one out. 70 passed through there, is what I'm saying.
You can tell now or.
No, you gotta think about it.
Okay, what do you think about it?
Maybe start writing down possible paths and that will help you.
Why?
Oh,
There's 70 different ones.
I know, but start writing one down. What can you do first?
4, 4.
Yeah, but tell me exactly the steps. So pretend I'm this
4 over 4.
little mouse,
Up
and
4
you're trying to give me
over
that.
4.
So you want me to go up, then what?
Up again.
Then up again, then what?
What?
then up again.
Then up again. So I went up, I went up, I went up, now I'm right here. Now where you telling me to go?
Up again.
Well, let's go to the right this time. Come on, get creative. So now I'm right there. Now let's go to the right again. Now I'm right there.
Oh.
Now let's go up. Now I'm right there. Now let's go to the right. Now I'm right there. Now let's go to the right. So I'm right there.
Choose the
Oh, so there was one way I could do it.
Is that right, dude? It's not too
No,
No, it's
Backtrack.
not.
no, that's a massive.
This one.
That's 256. It's only 70.
I was getting close though.
By backtracking, you also mean you can't go down and you can't go to the left.
That's why I said shortest path.
So it's always 8.
So you'll never go down or to the left.
So it's u plus r to the power of 8.
No. 4 plus 4 is 8 to the power of 8.
No, u plus r.
Yeah, maybe I don't know what U is.
U plus r. You're the one that wrote it.
You being up and then or being to the right.
It's to the 8. Give me the number that's supposed to be, because I don't know what that number is.
What?
How many paths can I make? Starting here, ending here. If I'm only allowed to make 8 moves, I guess. How many shortest paths?
Count 30. I don't know what you want for
Well, I wanted to come up with a way to think about it. Okay, let's try another path. Let's see. I could have gone to the right, and then up, and then up, and then up, and then up, and then to the right, and then to the right, and then to the right. Oh, there's another possible one. Right?
Right.
How many of these paths can I write out? In other words, how many arrangements of these letters can I
Right, that's what I'm
get?
thinking
So what's the
That's what
answer?
I'm thinking of, but I don't know.
That's what I'm thinking of.
If all these letters were unique, how many ways could I do it?
8 factorial.
8 factorial. And then what's in the denominator? How many ways, different ways can I arrange the r's?
4.
4 factorial.
Why is it just the r's?
And how many different ways can I arrange the u's? 4
4.
factorial. It's the exact same thing as going back to that, what was that word? Avrock or something?
Aardvark.
Aardvark?
No, that's what I was looking at, but
Aardvark.
Aardvark.
There it is.
Advert.
Aardvark, with 2 a's at the start. So it's just 8 factorial over 4 factorial over 4 factorial.
And, okay, I know we just talked about this, but I think I'm missing it still.
Okay. Numerator. How many arrangements as if it were all different?
The
Denominator. Divided by how many arrangements we get that give us the same thing. How many ways can I get this exact same thing? 4 factorial times 4 factorial. If I require that and r goes here, u goes here, u goes here, u goes here, u goes here, and r goes here, and r goes here, and r goes here, then there's 4 factorial. How many options do I have for the first r? 4 for the second r. 3 for the third r. 2 for the last r. 1. 4 times 3 times 2 times 1.
same thing for the
How many options do I have for the first u? 4, 3, 2, 1.
Oh, okay.
So the size of the equivalence class is 4 factorial times 4 factorial. There's 8 factorial total arrangements if they were all different. Therefore, there's this many paths. Isn't that kind of a cool problem?
What? Okay, so the bottom one says all the ones that are the exact same.
Here you are in the
No, that
city,
makes sense. That
and you
makes
need to get
sense.
from point A to point B. And the answer to how many ways that you can do that without backtracking is equivalent to asking how many arrangements can I make of those letters that are unique.
So that's what you meant when you reading tasks. We can do problems like that reading tasks, because for
Yeah, you find things that are completely unrelated, that seem completely unrelated, that turns out are the exact same question.
okay, I'm you lost me.
Imagine you were in a city,
Okay,
like this,
yeah, we got it.
and someone asked you, how many different paths could we take to get from here to here
And you could tell
without backtracking?
them. Right.
And you sit there and you think for a second in your head, let's see, that's 8 factorial over 4 factorial over 4 factorial. Oh, that's 70. And you tell them 70. They're like, what the F?
Right.
What did you just do?
Those aren't unrelated though.
They seem unrelated to that person.
Oh, okay, that's
The arrangement of letters, what does this have to do with this?
Okay, that makes more sense. Okay.
And so that's the reason that the author is showing this at you. Is it's something that seems completely unrelated that you just went over.
Right.
Is that why there's freaking word problems in our homework?
Not necessarily. Sometimes you just need words to
No,
communicate
it's
the
that
problem.
in this. In 17 sections.
Oh, I'm sure, yeah. The majority of what he's going to be asking is probably going to be questions focused this way. But that's the end of new material. So, you can start homework, you can ask me any questions.
Do you want to redid homework?
I sure do if you redid it. I said today was the only day I was going to take it.